So, yesterday we have seen some. I think it is not forwarded to you. I think yes, it is forwarded. Yeah. So, readers and writers problem. I think it is. We have seen. I think it is not. It is not actually. So yesterday I have introduced what exactly the memory protection of so-called memory management schemes and all those things have been discussed in the previous class. Today I'd like to talk about two issues, two very important issues. Number one, I'd like to talk on number one. First one is contiguous memory allocation is the first one. Contiguous memory allocation and memory allocation. And the second one is paging. Second one is paging. Okay, these are the two concepts I'd like to discuss today. What exactly these two will be and how these two will be organized by your operating system and how the memory can be allocated among several number of processes will be given by this particular these two different types of course many other things are there, but these two are basic things where we would like to see into memory management schemes. First one is before going to take contiguous memory allocation, we must get some kind of clarity regarding to continuous and contiguous. That clarity is very important. What do you mean by continuous and what do you mean by contiguous? Continuous means, let me give you one particular quick example. So let us consider, as far as memory is concerned, so let me draw in general square boxes, something like this. So this is memory. So within this particular scheme of memory, so let me consider this is 1 byte, second byte, third byte, fourth byte, and so on and so forth. You do have every line. I mean, every box will be considered as 1 byte. 1 byte, 8 bits of information is going to store within this particular location here. So that is my intention here. So 1 byte, and so on. Now, this particular address of these bits will be seems like this. For example, this is 0 in the sense immediate one is 1, immediate one is 2, immediate one is 3, and so on and so forth. 4, so 5, 6, and so on and so forth. This sequential arrangement of bytes will be called as continuous. This is called as continuous. Sequential arrangement of bytes will be called as continuous. Whereas a contiguous, hope that you do get the point here. Whereas a contiguous, when using one particular language, whatever the language you can use, one particular language, you may be declare a particular variable something like this integer some x of some 20. An array can be declared by you. An array can be declared by you. Now, as far as our basic idea regarding to any kind of language, look at this. Integer could be gets occupied 2 bytes in memory. I'm talking about C programming only. Don't consider any other kind of languages. So 2 bytes only. So 2 bytes in the sense each and every index value of this x is occupied 2 bytes here. Let me take into consideration of so this particular arrangement or allocation of memory for the array is So you can see these two bytes will be considered as one particular so item, that is A of 0, and the rest two will be considered as the next item of array A of 1. Okay, let me write in terms of like this here. So I'm unable to write properly. So A of okay, x of so let me consider like this here, x of 0. Let me write something like this. These two will be considered as x of 1. These two will be considered as x of 2, and so on and so forth. This is the way which is being allocated. What I have specified in blue color, that allocation should be seen something like this. Then here I'd like to mention that what is the address of the first what you call first array element is, in the sense 0 is the address of first array element. So 2 is the address of second array element. 4 is the address of third array element. 6 is the address of so let we can consider what is that, x of fourth element, and so on and so forth. In this way, addresses will be considered here. Now you can understand there is no information regarding to so address 1 is not existed when an array was allocated. Address 3 was not considered or existed when array was allocated, and so on and so forth. So this allocation is called as contiguous. This allocation is called as contiguous. Contiguous means it could be allocated a group of bytes as a single unit. A group of bytes as a single unit. That is called as a contiguous. So this allocation is called as a contiguous. Please understand what is a contiguous first. If you do understand this particular contiguous in a proper way, then what I am speaking is very, very easy to understand. It's very important for you. Okay. So that is that allocation. So 0 to 2 is one item, 2 to 4 is another item, 4 to 6 is another item, 6 to 8 is another item, and so on. And here, as far as a continuous, first byte, you don't have any information regarding to first byte in contiguous. Third byte, it doesn't. It is mixed with the x of 1. X of 2 will be taken fifth byte. X of 3 will be taken seventh byte, and so on and so forth. For example, as far as the example I have given here. So that is what you need to understand. What is the contiguous? Okay, hope that it is understand by you. Do you
Yes,
understand
sir.
this one? This contiguous understand is very important while talking something about what you call contiguous memory allocation. Now, we'll come to actual thing here. Before going to take contiguous allocation, let me talk something about so actual memory orientation. Already last class also I have given the same, but right now I'd like to take the same thing again, because it's our duty to explain something regarding to so contiguous memory allocation. For example, this is memory. This is the memory here. So this particular memory so will be so starting with so 0 to let me say for our convenience, not my, for our convenience, let me say this is 10,000. So totally 10,000 locations are available with us. 10,000 locations are available with us. Most of the operating systems, let me say Unix, Linux, or somewhere else, all other operating systems are supposed to be stored their operating system in random access memory. Let me call it as RAM. It is RAM, random access memory. So their random access memory can be stored in lower addresses. Let me say this is the place where exactly operating system was resided, and there is one particular register. That register is considered as a base register. This base register is trying to always protect the operating system's location, because while we are trying to assign or allocate any memory, by operating system, it must be always greater than base register of the operating system. Okay, thereby it is being allocated. Now, as far as a contiguous allocation, what exactly it is supposed to be done? What exactly it is supposed to be done? What you understood regarding to, memory protection, while contiguous allocation is going to be taken into consideration here. So let me give you the memory protection will be always, before going to take this memory protection, I'd like to ask a question, all of you 6 people, that what is logical address and what is physical address? Unmute yourself and answer me. Najupo. The address space which is being provided by CPU is called as logical address space. Then physical address space.
Physical address space is the address generated by memory management unit.
With physical address not exactly generated, will be available within the memory. Memory management will be always, memory management unit will be identify the address, not generated. It should not be generated anything. But CPU can be generate the addresses. Okay, the addresses which are available within the random access memory are called as physical addresses, and the process where exactly has been stored right from the beginning to ending of that particular process will be called as physical address space. Okay, you need to understand this one first because already we have discussed in the previous class itself. Any deviation or it is okay?
Okay, sir.
Now, so CPU is always generated logical address. So here, how the protection will be taken into consideration here is already we had a discussion regarding to relocation register. Already we have one particular information with us, that is relocation register. Relocation register is the smallest memory. Relocation register content will be smallest address where the process will be get stored. Smallest address where the process has been stored. Relocation register's address will be smallest address value where the process was stored. Smallest address in the sense. So let me draw something here for you, then you could understand what I'm speaking. For example, your process 1 can be stored right away from here to here, for example. That is the process P1. Okay, will be starts at 200 H and will be ends at 700 H, for example. So out of this, the smallest address location will be 200 H. This 200 H will be considered as relocation register. This value can be stored in relocation register. Simply speaking, where the process has been started, that is the relocation register. And limit register, another point will be there, limit register. One more thing is there here, limit register. Okay, this limit register is supposed to be stored. What is the size of your process as far as logical address is concerned? Size of your process, size of the process as far as the logical address space is considered. So here you can consider this particular allocation what I have given here. So 200H to 700H will be the total memory which is occupied by P1 here. So P1 has size of P1 as 500H or 500 kilobytes. Let me say each kilobyte will be one H. Then 500 kilobytes are required to store your P1. So therefore, this 500 will be the limit register value. This 500 will be the limit register value. Okay, 200 will be the relocation register value. So where limit register value should be the size of your process, whereas relocation registers address will be, I mean relocation registers content will be straight away address of the physical memory. It is not address of the physical memory, it is the size of your size of the process, the process. Okay, that's what you need to remember. Whereas this one is straight away address. It one is straight away address here. Therefore, this limit register and relocation registers are supposed to be used for managing the hardware protection, hardware support for protection, memory protection. These two are supposed to be used. Now, so let me draw a small diagram for you to understand in a proper way. To understand in a proper way, let me draw the same diagram. Actually, I don't want to take any other kind of diagram. So look at this. This particular thing is operating system where exactly it's been stored. So here it is 0, here it is 0H, and here it is 200H, and here it is for our convenience. As I said that this is 10,000H. 10,000H. Let me consider, because we'd like to take some kind of activity here. So now, already I have told you limit register is the size of your process, and the relocation register is starting address of the particular process here. Now, CPU can be generates a logical address. Logical address is being generated. Logical address can be generated. This logical address must be, whatever the logical address which was generated by the CPU, it must be always less than the content of the limit register. Content of the limit register. Content of the limit register. Okay. If it is not, if content of the limit register cannot be, I mean, limit register might be having the size of the particular what you call process. So if it is not less than the limit register value, then obviously it will be considered as trap. So trap in the sense, so addressing error. Addressing error. What is this? Okay. Addressing error. Now, if it is true, for example, if it is false in the sense, that is the point here. If it is true, there is no problem. It will be continued. That is true. Will be continued. Added with relocation registers value. Added with relocation register value. Okay. Then after adding this relocation registers value, then it will be identify the physical address. Physical address. This is the memory protection for contiguous memory. So let me give you one quick example, then you could understand what I am speaking this one here. So CPU wants to, not CPU, sorry, operating system wants to, allocate some space or memory for a particular process. Let me consider this is the area where exactly operating system has allocates one particular process into the memory here. So let me say this is process P1, and so at 700 H, it has been started to store this process P1. It occupies approximately 950 H. So totally 250 kilobytes are required. 250 kilobytes are required. Therefore, so limit register's address will be, value will be 250 kilobytes. 250 kilobytes. And the relocation register's value will be, so relocation register value will be equal to 700 H. And logical address space will be, let me write here, logical address space. Logical address space will be okay. Logical address space will be, so this could be, I mean, CPU can able to generate, let me say, so some 0 kilobyte to so 250 kilobytes. This is the logical address space. So it could be generate 0, 1, 2, 3, 4, 5, 6, and so on. Each kilobyte will be used, each kilobyte can be used to store one instruction. So the condition is, as far as our convenience, I am talking. So each kilobyte, each kilobyte is used to store one instruction, only one instruction, one INSTR, one instruction. Only single instruction is going to be stored in each kilobyte. For our convenience, I am talking everything. So that is why we do have 250 instructions are there with you. 250 instructions are there with you. Now, so look at this particular point here, whether this particular entire diagram will be satisfies our so conditions or not. Let us have a look here. Now CPU has generated some so 25th address, that is 25H was generated. Does 25 is less than, let me take some other color, then it is very easy to recognize. So 25 is less than so 250. Yes, it is true. Since it is true, you just move this way. You just move this way. For this 25, what you are trying to add, relocation register address. So relocation register address is 700. So 700 plus 25 will be taken. 725 H will be the address where exactly CPU wants to execute. Somewhere else here it is 725 has been so stored here. This is, let me say, this is 725 H. The instruction which is resided at this particular place will be taken from the, I mean, load from the so physical memory to the CPU, and that can be executed. If it is completed, then immediately CPU can be generate one more address. So the same protection will be continuously gets operated. Same protection can be continuously gets operated. Any questions so far? Any questions so far?
No, sir.
All others?
No, sir.
Leda?
No, sir.
So this is the way the memory protection is being happened. Memory protection can be happened something like this for allocating the processes in contiguous manner. Contiguous manner. So to execute the processes, it would be maintained a particular so process allocation table. Process allocation table will be maintained. Let me give you what is that process allocation table after some time. Let me talk about now. Let me talk about the contiguous allocation here. Okay, contiguous allocation here. Let me talk about that. So contiguous allocation does means if you do have so this memory in the initial stages, the entire memory can be considered as a single whole. Entire memory can be considered as a single whole. As I said just before, So the memory can be always, lowest memory can be always taken by, this lowest memory can be always taken by operating system, and 0H2, so 200H, so will be taken care by, so operating system. Now, and as far as our convenience, as I said that this will be 10,000 H, 10,000 H, and 200 to 10,000 H approximately 9800 H will be 9800 H will be available as a single block. It is as available as a single block. Okay, as far as the textbooks, it is not at all a block; it is a whole. Okay, textbooks, it can be termed as a whole, available as a single whole. This 9,800 H will be considered as a single whole. Now, in this context, there are certain number of processes which are available in the ready queue. There are certain number of processes which are available in the ready queue. Let me say process one does need some 150 kilobytes to store. Process 2 does needs some 200 kilobytes to store. Process 3 does needs some 75 kilobytes to store. Process 4, let me wait for a while. Let me take somewhat user values because it is 10,000, it is 10,000. Sorry for this, 10,000. So that is why it is some 1500 kilobytes are required, 1500 kilobytes. It will be taken approximately some 2500 kilobytes are required here. So 750 kilobytes are required here to store. P4 will be taken, let me say, 5000 kilobytes. 5000 kilobytes are required. Let me wait for a while. 5,000, 5,750. How much is left over? Yes. Next one is 9,500 minus 5,750, 4,000 something. Okay. However, next one is, let me erase this one and let me take one more. Let me take another one. So let me take another value here. So 4,250 kilobytes are required to store to execute the entire process of P4. So P5 will be allocates. Let me say um, 1,350 kilobytes are required, and P6 will be taken. 650 kilobytes are required to store, and P7 will be taken. So 3,570 kilobytes are required. So for example, these are the processes which are available, so within the memory. So here you just mentioned 10,000, then only the application is so easy to understand. Otherwise, it could not. Now you can see. So P1 is allocated. P1 is required approximately 1,500 kilobytes. So P2 is allocated. So P2 is required, not allocated. Required 2,500, and P3 is required. So 750. So P4 is required 4,250. P5 1,350. P6 650. So P7 3,570 kilobytes are required. Now, so the memory, physical memory, which is being seen in this on the screen, will be available as a single hole right from 2000 H to 10,000 H. That is 9,800 H is available as a single hole. Now, based on the allocation of these processes, the entire memory can be divided into several number of holes having different sizes, not exactly same size, different sizes. So, based on the allocation of the processes, by operating system, the entire memory can be based on the allocation of the processes in the by the operating system. Entire memory can be divided into several holes having different sizes. So this is what happened when we'd like to take into allocation. Allocation will be took place by the operating system. Entire large hole will be divided into several subholes. And what are the sizes of each hole in the sense? Based on the allocation of the processes. For example, P1, P2, P3, P4 are all these processes are available in the ready queue in the same order. Now, for this particular session, first hole size is 1500, second hole size is 2500, third hole size is 750, fourth hole is 4250. We don't know whether fifth hole will be allocated or not. Now, if allocation could be took place, what would be happen? Let us see this particular allocation here. 200 H2, this allocation could be always happen lower memory level to higher memory level only. Please remember this, lower memory level to higher memory level only. So therefore, first one is 1500 H. So 1500 H plus previous value will be 200 H. So total 1500 plus 200 will be 1700 H will be the last and final address of the process P1. It is being allocated. So totally the size of this one is 1500. Now 2500. So wanted to allocate 2500 in the sense. So 3200. No, 4200 I think it is. 4200 is the correct value. Am I correct? So 2500 plus 1700. So totally, yeah, 4200 is the particular location where particular value which is required. 4200. Let me draw somewhat bigger. Okay, this is 4200 H is the last and final address by process P2. Okay, the total size of this particular area is 2500. Okay, 2500 is the total area where exactly P2 is occupied. So 4950 because the process P3 will be this one. So therefore, it is starting at 4200 and 750 is required. So therefore, 4950 H will be the final address of process P3. Let me say the size of this particular thing is 750. Whatever the size you have given by the process size, the same size will be mentioned at this place here. Okay. Use some other color, then you can understand. I'll give you some time for drawing this particular same thing. I will give you some time. Okay. However, 4250. Then what is the final address? 4950 plus 4250. So it will be 9200. So look at this. This is 9200. This hole is very big enough. Let me draw here. Okay, let me draw somewhere else. This hole is very big enough. When compared to the previous one. So this is process P4. Process P4 will be taken. What is the value? 9000. Please remind me.
9200.
9200. So this is 9200. 9,200 H. The size of this particular thing is 4250. 4250. So allocation was over. Then next coming thing is process will be this one here, process P5. This P5 cannot be allocated because we do remain with, let me take some other color, then you could understand. We do remain with only 800. This space will be called as, this space will be, available space will be 800 kilobytes, which is remained here, which is not able to fit with 1350. So therefore, total number of allocations by your operating system could be, so 4. First whole size is 1500, second whole size is 2500, third whole size is 750, fourth whole size is 4250, and the final whole which was not allocated to any kind of thing, so that is 800 kilobytes. So here you may be asked one question to me. That question is 650. Why this could not be allocated? Because that is arrived after P5. That is arrived after P5. So it should not be allocated immediately. After P5, then only P6. Okay. After P5, then only P6. This is the allocation. So entire whole will be divided into several partitions. Now you can see the partition where exactly which is remained, this particular partition is called as fragmentation.